So looking at Spark V7 and subsequent V8, V9 as well, but specifically, I guess V7 and V8 because they were both 32-bit, right? And then V9
Yes.
brought 64-bit. So
Right.
there were a couple of like looking through the architecture manuals, there are a couple of features or design decisions that kind of stick out to me as maybe not unique, right? They take inspiration from elsewhere, but they're decisions that y'all made to include this functionality. So I'll list them off and then let you kind of choose which one you want to start with.
Okay.
But register windows we already mentioned, the branch delay slot and some of the functionality around that with different variations of instructions you could put in there, and then the alternate address space and using the address space identifiers.
Okay, well, don't get too far ahead of me.
Okay,
Let's start with the register window. So,
okay, let's do it.
yeah, so I asked that question. I said, why are we going to stick with register windows? And, they had been clearly invented and articulated at Berkeley with the RISC 1 and 2. In fact, it was a master's student. I had forgotten about this, but it was two master's students, Halbert and Kessler, in a master's student project had actually proposed them at Berkeley. Chuck Seitz had talked about what to do with 1,000 registers, and AT&T
Right.
was doing research on a lot of registers. The whole idea is that you don't need to, if you have a small number of registers and you're doing a lot of procedure calls, you have to save them right away and reload them when you come back to your procedure. So why waste all that bandwidth to the main memory or cache when you can just stick them on a little local register cache
Right.
and have overlapping windows so that outs can become ins, and it just, it reduced the number of loads and stores. But compiler technology had advanced. Certainly on the 801 project, forgot his name, had done better optimizing compilers. How can you use a fixed number of registers like 16 and keep items there for multiple procedures at the same time? So you have to do cross-procedure register allocation, or register coloring, as they called it.
Right.
And that made the compilers very complex. So here we are, a little startup company. It's hard to imagine we were a small startup company.
Right.
There were two people in the compiler group, and there was Steve Munchnick from HP. And HP had a RISC project. They were actually slightly ahead of us, called Spectrum at the time. It later became Precision. Steve was extremely closed-mouthed. He was scared about saying anything about HP's project with us. He was very, closed lip, and I think properly so. But anyways, so one day I called a meeting. So on my left was Steve Munchnick, and on my right was Dave Patterson. And I said, "Are we going to do Windows or not?" And I turned to Steve Munchnick, and he said, "Well, if we're going to do cross procedure call register coloring,
Right.
I need two more people." And so, and I turned to Patterson and I said, "Well, we kind of get that reduction in load stores automatically with Windows."
Right.
So I said, "Okay, decision done,"
Right.
and we stuck with Windows. So
And
that's how it happened.
there was a well, I don't know if this was unique, but not all register window architectures did it this way, where y'all had explicit save and restore instructions, right? Rather
Yeah,
than
that was a feature that we did. The original Berkeley, when you did a call, it changed the window pointer.
right.
And a return decrement on it. So one of the OS guys, it could have been Steve Kleiman, who later became the CTO of NetAmp. Steve, I think it was Steve, suggested that we decouple the two. Why not have a separate way to move the window pointer? That way you could do things like tail recursion elimination.
Mm-hmm.
You don't have to advance the window pointer if you don't want to. In fact, you could actually make it a traditional fixed register machine if you wanted to. Just never increment it.
Right.
Yeah, go for it. So that was really an important change that helped keep Windows going for so many decades at Sun, because when you start doing the pipelines and the very faster designs, a large 300 register file might seem pretty big to do in one cycle. And so by separating the two, and especially if the change happened in the previous instruction, or at least you could schedule the instructions, you could actually maybe start the process of reading out a row early, either by caching a whole window in one cycle or by just charging the row early and reading it out. It's a two-step memory access, SRAM access in the chip. So by decoupling those two, that was a good idea.
And there was a large number of registers, but they weren't infinite, right? So if you did enough procedure calls, you'd eventually run out.
You had to spill and refill, right? So if you're going up and down the stack a lot, the programs we looked at tended to go within a range. Maybe you'd bump up here and go like this, and go down here and go like this. So it does count on not zipping down the call chain and zipping all the way back,
right?
More than eight windows. But that seemed to be the behavior at the time, at least. And object-oriented languages like Smalltalk really benefited because there you couldn't allocate anything across procedures.
Right.
So, for those type of environments, they were a real win. But, compiler technology by today, the RISC-V obviously is just a fixed number of registers, so people feel. In reality, the memory system ends up dominating performance. So today we have first, second, third level caches, maybe fourth level caches, so that not all ends up. Memory has historically dominated von Neumann designs.
Right.
I hate the word von Neumann, but he's a great guy, so we still use it. Computer designs.
Right. So any other?
You mentioned delay slots.
Yeah.
So that actually came from microcode. The microcode we had in the Alto and many microcoded machines had a delay slot. So, since you have to fetch, where you're going, that's going to take another cycle. Why not do something?
Right.
More, this is a primitive form of threading with no overhead, essentially. So it seemed like a no-brainer to do delay slots. Now, I added the annul feature, which you could turn on a bit in the branch so that if you don't really have anything to put there, it would not do it.
Right.
Not execute anything. And so you could save code space and execution time in more sophisticated pipelines later. So the annul bit is a way just to do a normal branch.
Right.
So you get it both ways that way. And I'm sure that the future pipelines were happy with that.
Right. And so just to kind of dig into the different options you could have for leveraging that delay slot, the most naive thing you could do is just put a no op instruction in there, right? And
that would be a total waste. So the compiler was really tried to move something there that is independent of which way you branched.
Right. But you did have to be cognizant of what you were moving there and how it impacted it, right? Because if you were, I think I was reading some literature from that time, and it was talking about if you are doing an unconditional branch, then you could move whatever instruction was right before the branch to after it, and that would be an optimization. If you're doing a conditional one, you could move an instruction from wherever the target was up to just after that conditional branch. And then I assume if you set the annul bit, then if the branch is not taken, the instruction is annulled. Is that right?
Yep.
Okay.
Yep.
And then I also read about let me look in my notes here, the delayed control transfer instruction couple, where you have a branch and then in the delay slot you have a branch. and that gets a little bit more complex, right?
Elected to leave that undefined.
Yeah. right.
A little hole in the architecture, but the compiler just never did it, and people weren't doing hand code. So, because the problem you could define it, what would happen, but we didn't want to constrain future implementations to whatever that definition was. So we just said undefined. Don't do it.
In the instruction set, it was undefined, or in the hardware? Because I saw that in the
architecture. In the architecture, we said this will result in undefined outcomes.
Okay. So
don't do it. There were a few other little tiny things like that in the architecture which aren't clean, but hey, this is reality. This shit happens.
Right.
Another one was floating point underflow. Really, IEEE would prefer not, but a lot of people want to round to zero. So there was a bit that, and it may not be consistent in all implementations. I mean, not all implementations may not implement it.
Right.
That kind of thing.
The other one that the other feature that I kind of read a little bit about and researched was the alternate address spaces and the address space identifiers. Was that something that was
something I did. Yeah.
Okay.
Well, putting I/O devices in the address space seemed like the most sensible thing to do. I mean, Sun had a thing where they had an I/O MMU where devices could go through that to get their virtual address, and putting devices in the address space seemed like the simplest, most straightforward thing to do. And we had a lot, because the ASI field was 8 bits, I think. You could have a lot of alternative address spaces, and we used it for all kinds of things. One of the key insights that I brought, and the OS people support it, in the definition of the SPARC architecture, was really to find something that applications and users see, and don't get hung up on what the OS needs. For instance, we did not define an MMU. Our first implementation used Andy Bechtolsheim's brilliant MMU design. One of the things I'll talk about that for a moment. One of the things Sun was known for in his very first Sun 1 and Sun 2 the Sun 2, was you put an MMU in node cache DRAM. You address it in 2 phases: the row address and column address. So he would send out the low order bits immediately for the row address. And then while the DRAM is accessing the row internally, he would translate the upper bits into, from a virtual number to a physical number in a table in SRAM chips. And then supply those bits for the column address.
Right.
So that meant he had a zero cost MMU. It took 0 cycles. In other words, it added no time to the memory access. And a nice hack. And we actually implemented that in the first SPARC chip. So I in addition to the architecture, I co-designed the hardware. This is a startup, right? You do more than one thing.
Right.
And you work 23 hours a day. So I designed the CPU part, the processor part of the Sun 4 board. I do have a Sun 4 board here. Notice how the board's got bigger.
Right.
It occupies the entire screen. Wow. We can get into the components on it later. But in the Sun 4 board, to get a single cycle cache, who wants set associativity and TLBs and all that stuff in the way? So it's a virtually addressed cache. So the bits come right out of the integer unit, directly access the cache. In fact, I patented this idea where the bits come out unregistered, just wiggling away, and then I have a solid advanced Schottky TTL AS374 latch them and drive all the cache chips to get a single cycle cache with all these 16 plus tag chips out there. And we actually patented that idea. HP had a similar thing. They had a flow-through latch, which addressed the cache. So really, that was a huge difference from the Motorola 68020. The clock to output delay time on a 68020 is like 20 nanoseconds.
Oh, wow. Yeah.
Yeah. What happened to our...
Right.
We need a 60 nanosecond cycle time. We've already lost a third of it just getting off the chip.
Right.
And so by wiggling the chips and registering in an external beefy registered device and then driving the cache, that helped us achieve the single cycle cache and virtually addressed. Well, you still want to map multiple virtual addresses together. So we implemented Andy's MMU, and we said, if you want to address virtual addresses, if you want to map them together, they have to equal modulo the cache size. So they have to be, the low order bits have to match the cache size. And then we'll have a tag bits on the side. We'll check the physical high order bits to see if they're different or not. And if they're the same, we know it's the same location. So,
wow.
So Andy's MMU saved us there too.
Right.
But I knew about TLBs, translation look-aside buffers.
Right.
You just couldn't implement it at that time. And at Xerox, when we did the Xerox Star, the virtual to memory translation was in main memory.
Mm-hmm.
So if you ever wanted to do a virtual access, you had to first access the translation table, then access memory. So actually, every memory access was 6 cycles, 2 slots.
Right.
That's one reason why the Star was so slow, relatively speaking.
Right.
So I knew that there's no reason to formalize it on TLB or MMU. So that, for instance, HP made the opposite decision. They formalized on the MMU management unit, and they formalized on I/O devices. And I thought that was a mistake. So that's an example of how having the system people there, they said, fine, because the kernel's going to change with every system anyways. And the kernel's the only person that cares about this stuff. It's just a mess. I/O is a mess. We're not aware of it so much now, but every possible I/O device you may ever plug into your computer back then and today, you have to have the device driver preloaded as part of the kernel image. It's got to be gigabytes by now. Anyway, so because it's so tied to the hardware, there was no reason to put it in the instruction architecture.